Okay, ladies and gentlemen, yes, welcome to this week's Monsoon seminar series. Our host, our speaker this week is Kaustubh Thirumalai from the University of Arizona. Cal did his... Okay, ladies and gentlemen, yes, welcome to this week's Monsoon seminar series. Sorry about that. Yes, he did his PhD at the University of Texas at Austin. He originally did a bachelor's degree at the National Institute of Technology in Karnataka in India. He was a postdoc at Brown University, and now he's an assistant professor at the University of Arizona. And let me hand over to him. He's going to talk to us about extreme Indian paleo monsoon. So Cal, please take it away.
All right. Hopefully everyone can hear me and see the screen okay. Thanks to the organizers for putting this together. Really, it's been incredible following along all of the diverse takes on the monsoon as part of this seminar. So thanks to Tara, Peter, and Liviu for organizing, and all the other board members and organizers as well. So today, I'm going to be talking about results from Expedition 353, which we sailed on. And my talk is titled Extreme Indian Paleomonsoon States and Productivity Collapses in the Bay of Bengal since the Last Glacial Maximum. First off, I'd like to thank all my co-authors, because it does take a village for generating these records and really getting to the bottom of what they can actually tell us and what they're telling us about the future particularly. So thanks to all my co-authors, Steve Clemens at Brown University, Yair Rosenthal at Rutgers, my student Serena Conde at the University of Arizona, Stephanie Desprat at CNRS, Liping Zhu at Peking University, Liviu Jiosan at Hui, Arvind Singh at PRL, Kaikshuan Bu at Rutgers as well, and Vimal Mishra at the Indian Institute of Technology, Gandhinagar. So these are my co-authors. I'd like to acknowledge their efforts for this work as well. And like I said, it does take a village. So I'd also like to acknowledge all of my staff scientists on Expedition 353, staff scientists as well as the scientists who sailed with us. And thanks also to all of the personnel on the JOIDES and IODP for making this work possible. So it really comes down to a lot of people for this type of work. Speaking of people, one of the major motivations for my work is based on this particular graph right here. So the circle that you see inside there, more people live inside that circle. It's about 51.4% as opposed to outside. And as we all know here, these are areas that are heavily influenced by monsoon winds and monsoon rainfall. And so Asian monsoon and Indian monsoon variability really impacts many of these countries that are super densely populated. And furthermore, these are places where the GDP is directly tied to agricultural output, which is again then related to changes and variability in the monsoon. So historically, the term monsoon comes from the Arabic word for season, mawsum. And here's just a map from the 1600s, actually, from the Portuguese. And Portuguese sailors basically took this term and brought it to the Western world. And essentially what monsoons talk about are these seasonal reversal of winds coming in from the southwest during summer, and then reversing during the winter and going from the northeast, blowing from the northeast to the southwest during the northeastern monsoon. And these wind reversals basically bring in seasonal rainfall changes as well. And so this is where that term really comes from. Monsoon is originally denoted to talk about the wind reversals. But as we've seen before in these seminars, really what matters to the people on the ground is rainfall. And monsoon changes have really captivated and sort of permeated the culture of the Indian subcontinent. I just thought this was pretty neat. Here's a photo I took while I was out at sea in the Bay of Bengal, looking at these storms that are sucking up water and basically evaporating and then dumping water on top of the Bay of Bengal. And then here's this really nice painting from the Ramayana version of Tulsidas. And you can see here the depiction of the monsoonal circulation shown here. And I really am captivated by this quote from the Ramayana, which basically says, "For months, the sky drank the ocean's water, sucking it up through the sun's rays, and now gives birth to a liquid offspring, the elixir of life." So we had atmospheric scientists talking about this stuff a long time ago. But the monsoon has dire consequences and rather large disproportionate impacts on several of the millions to billions of people living in this region. So here are just some images of both monsoon excesses as well as monsoon failures that really have an impact on folks who are living in the subcontinent. And as I was saying, the agricultural production of many of these countries, here's an example from India, is really coupled to changes in the monsoon. So this is just intraannual variability of the monsoon in pink, and the percentage change in agricultural production in green right there. Okay, so what does the rainfall signature of the monsoon really look like? So here is a animation that I put together from the ERA reanalysis data set. And essentially what we're seeing is the march of the Indian monsoon over the seasonal cycle. So this is basically looping from January till December. And essentially you can see that the monsoon rainfall envelops the Indian subcontinent during June, July, August, and September, and some parts of October. And then while retreating, there are parts of peninsular India that actually receive a substantial amount of rainfall during the winter months in October, November, December, and January. Now, just to give a scale of this, I think this really doesn't do justice to the scale of the Indian monsoon. I just put this together. Here's just the Indian country, not the subcontinent, but the country of India, superimposed on a scaled map of the United States. So you can think about this monsoon as affecting parts during the same time of the year, from all the way down to Mexico up till Saskatchewan in Canada, for those of you who are more familiar with American geography. So this is a huge phenomenon, and we want to understand what's going to happen in the future. And in particular, we want to try and sort of assess what pathway we're going to be taking, because changes in the monsoon, both if it's too much, if it's a stronger increase, or if it's a weakening, both of those phases are going to have large impacts that trickle down to the subcontinent. And so there have been several modeling studies carried out to figure out what's going to happen in the future. And here's just an example, the latest example from Katzenberger et al., published earlier this year. And this is a pretty comprehensive assessment of Indian monsoon rainfall under future warming and how its variability is going to change under CMIP 6. And the bottom line is that all of the models, which rarely happens, seem to agree that the Indian monsoon is going to strengthen and intensify by a lot. And the CMIP 6, which is the latest assessment of the climate model intercomparison project, essentially revises substantially some of the estimates coming from the previous versions from CMIP 5 and so on. And really, they're arguing for a really substantially strengthened monsoon seasonality in the future. So this is in millimeters per day, and you can see most of these models, and there's a whole bunch others. I would refer you to read this paper if you're interested in the details. But they're showing a significant increase on the order of about 3 millimeters per day as a whole on average, which would increase this access here on the observations. Okay, but the impacts of the monsoon are not just terrestrial. And as you can see here, in fact, there's a large component of monsoon rainfall over the Bay of Bengal and over the equatorial and tropical Indian Ocean regions as well. And this has strong impacts. So what I have right here is a seasonality, just like this seasonality right here, an animation of the seasonality of salinity in the adjacent oceans to the continent. So you can see here that basically during these June, July, August, September, we have peak monsoon over the Indian subcontinent. And you can see this freshwater plume running out from the Ganges, Brahmaputra, Meghna drainage region, and essentially sticking to the coast of India, this really, really fresh signature. And that peaks during October. Okay, so it takes about a month. There's a little bit of a lag, about a month from peak monsoon rainfall, peak riverine outflow, and then the salinity signatures in the Bay of Bengal. So you can see here, and in particular, what we see happening here is that there is a seasonal current here that goes equatorward called the East India Coastal Current that essentially carries all of this really, really fresh water. And then it ultimately dissipates and mixes into the greater Indian Ocean right here. And so if you take a look at this, these processes, these physical processes of monsoon outflow and subsequent impacts on the oceanography, they actually set up a very unique system right here that has unique physical properties. One of the really interesting aspects here is something known as the formation of the barrier layer. So if we zoom in to the Bay of Bengal, essentially this phenomenon of barrier layer formation in the ocean is defined as so the thickness of the barrier layer is defined as the difference between the isothermal layer depth. Okay, so that's what we would typically imagine to be a temperature-based mixed layer. So you can think of this right here as the mixed layer going up to about 90 meters. This is a figure taken from this paper by Lucas and Lindstrom that describes a profile from the Western Equatorial Pacific. Okay, so this is not in the Bay of Bengal. This is the Western Equatorial Pacific, which has a very deep thermal mixed layer. But there's another mixed layer that when you calculate using density, there is a mixed layer that's much shallower that is based on salinity. So in the Western Pacific, this happens because of rainfall directly. And you can see here that the density here mirrors the salinity profile and not necessarily the temperature profile, as would normally happen in on more average open ocean conditions. So essentially what you have here, the thickness of this barrier layer is the difference between the mixed layer calculated based on density and the mixed layer calculated based on temperature. And so Vinay Chandran in 2002 was the first person to actually report a barrier layer in the Bay of Bengal based on observations. Although earlier workers hinted at this and basically speculated that this existed. So you can see here, this is a profile from August 1999 right here in sort of the northern central Bay of Bengal. And you can see what I'm talking about right here, where this is density that is going down right here and mirrors the salinity profile. And remember this salinity, this really fresh water that's coming in from that runoff. So this mixed layer right here is the difference, is essentially the mixed layer calculated on the density, whereas the isothermal mixed layer depth or the isothermal layer depth, the temperature is constant. It's warmer as you go further down, giving rise to this barrier layer right here. So essentially the post-monsoon outflow into the Bay of Bengal today induces a barrier layer formation that imprints itself on the mean annual oceanographic conditions as well. And it can vary from anywhere from 15 meters to about 50 meters or even larger sometimes. And it can seasonally be eroded, which it happens as the monsoon recedes during the intermonsoons. That's where it's really strengthened. And then as the basically the seasonal cycle warms up again, the barrier layer disappears again. But the barrier layer is imprinted in the mean annual oceanography of the Bay of Bengal as well. So if we were to take a profile right here, essentially what we can see is that this would be a profile that kind of depicts it on the coastal part of India, where here is density in yellow, salinity is in blue, and then temperature is going to be here in red. And essentially, you can see here the same thing that was depicted, but in a more kind of idealized manner, that the isothermal layer depth is deeper than the mixed layer calculated from salinity and density. Okay, and why is this important? Well, not only does it inhibit mixing, but it inhibits productivity and primary production. So the barrier layer thickness is coupled to the, obviously to the vertical stratification. And the fact that vertical stratification is going to limit nutrients in this region, where nutrients are primarily sourced from the deep ocean, in fact, you're actually going to have significant impacts on productivity depending on the thickness of this barrier layer. So essentially, you can think about the barrier layer thickness as a way in which you inhibit mixing and you inhibit productivity in the Bay of Bengal. Unfortunately, we don't have very many observations of the barrier layer. So here's a paper by Taratil and others in 2008, where the sort of the lighter yellow colors depict a shallower barrier layer, and the more green colors depict a thicker barrier layer. And all the red dots are basically where we have observations from. And you can see kind of loosely moving from July to November. Mind you, these are seasonal. These are not really comprehensive data, so they're not seasonal cycles put together based on a bunch of data. However, if you use whatever you have for each one of these months, you can definitely see the sort of the deepening of the barrier layer as you move after the monsoon into the post-monsoon season during October and November. You can even kind of see the East India coastal current here. And what I've actually put down here is from this paper by Hussein and others that came out recently, is a satellite-based estimate of primary production in the Bay of Bengal. And loosely, what you can see right here as you move from the peak of the monsoons from July to the post-monsoon region, post-monsoon time, you're basically seeing a drop in the amount of primary production in the Bay of Bengal as you move into the post-monsoon seasons. And so primary production in this region is really promoted by this process of eddy pumping. Essentially, cyclonic gyres get set up during the southwest monsoon winds, and you both have nearshore as well as remote winds that contribute to eddy pumping of nutrients from the subsurface into the surface. But then when you hit the post-monsoon season, you get this barrier layer, and the primary production is basically suppressed by the barrier layer thickness. And actually then you have interior Ekman pumping that also limits the amount of nutrients that are sourced from the subsurface into the surface ocean, such that you really hit the deep chlorophyll maximum in the Bay of Bengal, and you limit primary production. So the monsoon essentially has a lot of downstream impacts here on the Bay of Bengal, and particularly in terms of primary production. And so we want to try and understand not only how the monsoon is going to change in the future, but also how its impacts are going to change. And so why do we really care that much about primary production in the first place? Well, this really comes down to fisheries. And in particular, it's a pretty staggering fact, but Bangladesh and India put together is the second largest fishery after China. And Bangladesh and India's fishery put together, it actually surpasses Japan, US, Russia combined, which is a pretty staggering sort of statistic. And moreover, it contributes to about 10% of the global fishery output as well. And a large portion of that comes from the Bay of Bengal. And you can see here this sort of dramatic image from a couple from last month right here. This particular fish is known as hilsa, and the hilsa is a really commercially important product, but also helps sustain several hundreds of millions of people. And this hilsa production is directly coupled to primary production, and in particular, you can kind of see here, here's the major fisheries across the Bay of Bengal. So including Myanmar, Thailand, India, and Bangladesh, you are essentially, we want to try and understand how this primary production is going to change, because that's going to have a huge impact on fisheries. It's already having a big impact where stocks are basically dwindling. So this is one of the major reasons that we need to try and understand how primary production and oceanographic processes, particularly physical oceanographic processes, how they can sort of piggyback onto the biological oceanography, and how it's going to affect these fisheries, particularly going in under anthropogenic warming. So what does that look like? Well, we have Earth system models, and particularly Earth system models that are enabled with biogeochemistry. And we can see right here, here's the, what I'm showing you right here is an image from this paper that really nicely summarizes CMIP6-based Earth system models for the future biogeochemical response to the Indian Ocean, or of the global oceans, I should say. So this is a metric of stratification. So it's the stratification index. More intense colors basically say where you have more stratification. This is the simulation for the historical period. And here are the simulations for two different scenarios in the future. And so the dots essentially represent where more than 80% of the models, there's about, I think there's about 26 models that go into this. So more than 80% of the models where they agree. So this is one scenario in the future, is another scenario, and more red is going to indicate more stratification. And you can basically see here that under the sort of the dire SSP 5 8.5 scenario, this is equivalent to the RCP 8.5 scenario, you can kind of see that all models robustly project increased stratification in the future. Okay. Now, on the flip side, here at the bottom is the net primary production that is, again, simulated by these models. And you can see here in the global oceans, there is not a lot of agreement between these models. And particularly so when you zoom into the Bay of Bengal, I apologize, you can't necessarily see it that big right here, but they're in fact projecting the ensemble mean, even though it is uncertain. They're actually projecting a increase in the net primary production despite projecting stratification. And so I should say that there's a lot of uncertainty in these processes. People are just beginning to start to validate and kind of really scrutinize some of these simulations as well. But bottom line is that the changes in net primary production and stratification do not seem to jive together according to these latest Earth system models. Okay, so here is my pivot and pitch for the geological record. And essentially the case that I'm trying to make here is that the geological record can furnish dynamical parallels essentially across altered mean states to really assess what entails the machinery of the Indian monsoon and moreover, its biogeochemical impacts. And for the group right here, obviously, by the geological record, I'm really talking about the deep sea record. And in particular, I'm going to be talking to you about results from Expedition 353 and drilling in the Bay of Bengal. So the time period that I'm going to focus on to look at these dynamical parallels and to look at altered mean states is essentially the most recent substantial global warming event outside anthropogenic global warming, which is the deglaciation. So the deglaciation essentially represents the movement of global climate state from a glaciated world from about 19 to 21,000 years ago to our interglacial world that we live in today. Okay, and we have to keep in mind that there are, while we're trying to infer some of these dynamic parallels, the forcings were completely different to what forcing, to anthropogenic forcing, for example. But at the same time, we have ways in which we can feed some of these boundary conditions into models, and hopefully we can try and make some type of assessments with proxy data as well. But essentially, there was a significant ice sheet in the Northern Hemisphere, and sea level was about 130 meters lower than today. Greenhouse gases were about 100 ppm lower than pre-industrial levels. And all of that changed as we moved from the last glacial maximum into the Holocene across the deglaciation. Okay, so I'm going to zoom into the Northern Indian Ocean, and I'm going to talk to you a little bit about our proxy approach. So this is a figure from a paper published earlier this year by my co-author, Steve Clemens. And you can basically see right here, this is our site, U1446, where our core comes from. This sort of purple box right here represents the sort of the large scale Ganges Brahmaputra Meghna drainage area. And essentially, if we take modern data sets of salinity and rainfall, you can kind of see here that rainfall in this box right here and salinity at the U1446 site are really closely coupled together. And this again comes from this inference that the post-monsoon outflow into the Bay of Bengal via the East India coastal current that conveys this sort of freshening signature. Our site it so happens strategically is located right in the midst of this East India coastal current as it comes down. Now, our site, the sediments from our site, I'm going to be, like I said, focusing on the last 20,000 years to present. So here's our age model based on radiocarbon measurements right here. We actually have a highly extended Holocene section, but even in the deglaciation, we have pretty high sedimentation rates here, such that we're able to actually look into the centennial scale variability of runoff. Okay, so we're gonna essentially try and reconstruct outflow, monsoon outflow, and link that back to rainfall on the continent. As you saw in some of those previous GIFs, even though you have peak monsoon precipitation over the Bay of Bengal during June to September, that salinity signature really comes in October, and it's the post-monsoon outflow. So we're sensing rainfall across this entire drainage basin. So a couple ways to kind of ground truth that. Here is GBM runoff in millimeters per month. As you can see, it peaks during the summer monsoon time. And what we have here, I'm not going to go into great detail here, but we do have pretty good observations of delta 18 of seawater so it's the stable oxygen isotope composition of the surface ocean waters. And even though they're a little spotty when it comes to the Mahanadi Basin where U1446 is located, for example, we don't necessarily have observations that are in August, for example, but when we take these observations and place it with either delta 18 seawater calculated from reanalysis salinity using a region-specific equation, they seem to match fairly well. And in another methodology, we actually used a sort of a theoretical delta 18 model, fed in the Ganges, Brahmaputra, Meghna runoff into that theoretical model. And that's what these pink triangles actually show us. And of course, this model is highly smooth and there's a lot of assumptions that go into it. But regardless, we're seeing some parity between these three different ways of trying to understand what the delta 18 seawater signature is at our site. And essentially, we can see that during September and October, really, we have sort of the delta 18 seawater minima that's corresponding to this GBM runoff right here. And the October delta 18 seawater signature is actually very strongly driving the mean annual delta 18 seawater signature. So here is a plot between October delta 18 seawater and mean annual delta 18 seawater at our site that's calculated from sea surface salinities. And essentially we see that October variability explains more than 70% of the mean annual delta 18 seawater signature at this site. So essentially, if we're able to somehow reconstruct mean annual delta 18 seawater, we can then track back October delta 18 seawater, which is a reflection of the overall runoff in the Ganges Brahmaputra. So how do we do that? Well, we are going to use planktic foraminifera. In particular, this particular bug right here is known as Globigerinoides ruber. We have sediment trap data in the Bay of Bengal that tells us that G. ruber lives throughout the year in these locations. And moreover, that they live in the upper maybe 30 meters or so. And so we have a very nice way to try and infer and reconstruct mean annual sea surface conditions using this particular bug. So here I just have from site U1446, the salinity seasonality, and here is the temperature seasonality. And if we use these sort of transfer functions that we've built over decades about planktic foraminiferal delta 18 relating that to sea surface temperature and the delta 18 of seawater, and then we also measure the magnesium to calcium ratios as an independent proxy of sea surface temperature with some influence of sea surface salinity. And then we have a region-specific East India coastal current delta 18 seawater signature, seawater relationship with salinity. So using these sets of equations, we can basically tease out the delta 18 seawater. And of course, we have to correct for the changes from glacial to interglacial delta 18 globally for ice volume changes as well, which we do. And if you recall, here is the all India rainfall signature right here in green that peaks during the summer monsoon months. And what I've done here in orange is using these equations, but using modern observations. If we forward model the carbonate delta-8 of forams that would theoretically calcify during these particular months, that is what this orange curve looks like. So how well are we doing? Well, we can compare our assessments and reconstructions from the core top to our forward modeled values. And so the mean SST at this location is about 28 degrees. We're doing pretty well with the core top. Same is the case with sea surface salinity. Mind you, I'm not going to be interpreting sea surface salinity as we go back in time, because people have shown that, and we've looked at it and seen that the sea surface salinity delta seawater relationship may not necessarily be stationary as you go back in time. So for the purposes of this talk, I'm going to be solely focusing on delta seawater, which is going to be positively correlated with sea surface salinity, as we saw earlier, with a higher delta seawater being associated with higher sea surface salinities. This orange right here, remember, is a combination of temperature as well as salinity. It's the calcite delta of Minifra. And so when we take a look at the measured core top value, we're actually doing really well when it comes to the expectation of the mean value of this calculated delta carbonate. And moreover, I'm going to be presenting some individual foraminiferal measurements or single shell measurements of foraminifera during particular periods of time. And the core top standard deviation of these individual foraminiferal measurements also matches well with the calculated 1 sigma of the forward modeled carbonate delta. So we're doing a good job where the mean values as well as the seasonality is being faithfully recorded in the foraminiferal calcite. And just as a plug here, we published a paper earlier last year where we actually performed some simulations to try and see whether this delta of single forams, or IFA, which is a short form for individual foraminiferal analysis, whether that's going to be more sensitive to temperature or salinity changes. And we basically see here, this is what is known as a quantile plot, where essentially here is calculated delta and here is an altered scenario where if they were exactly the same, they would fall on this 1:1 black line. But each one of these scenarios are different scenarios that have increased salinity seasonality or reduced temperature seasonality and so on. But the main take-home message here is that when you move towards the more negative side of the carbonate delta then we are much more sensitive to changes in runoff. So you can see here, these are salinity simulations that show a much larger range and deviation from the 1:1 line. But on the flip side, when you move towards the more positive carbonate delta values, we're actually going to be more sensitive to temperature, and we lose that sensitivity towards runoff. So this is going to be in the cold sort of winter seasons, maybe January, February, when we have the peak coldest temperatures. So this is an important thing to remember, that when you move towards the more negative side, it's more sensitive to runoff. Now, I did talk about primary production and paleo productivity. And so how are we going to look at that going back in time? Well, so for this work, we're actually proposing it's not necessarily a new paleo productivity proxy. People have inferred this before, but this is actually, we're piecing this together using multiple lines of evidence. So essentially, we're looking at the abundance of globorotallid species. So these are particular foraminifera that live in the subsurface, and we know that in the Bay of Bengal, in the coastal Bay of Bengal, they actually live somewhere close to the deep chlorophyll maximum. Here's just an image of one particular species of globorotallid. This is Globorotalia truncatulinoides. We caught these in the Gulf of Mexico. This particular species doesn't really exist in the Bay of Bengal, but I just wanted to show you this image right here to give you an idea of what these bugs actually look like. So we have things like Menardii or Hirsuta and Tumida in the Bay of Bengal that we're really counting and looking at their relative population abundance as a proxy for paleo productivity. And here's a couple lines of evidence as to why we think this is a productivity proxy. So here is a pretty remarkable paper from Spindler and others in 1984 in JFR. And essentially what they found was that they really could not feed live copepods, and they tried a variety of different zooplankton and as well. They could not feed them to these non-spinose species. So these are non-spinose foraminifera that don't have symbionts, sensu stricto, like the rubers or these other bugs that live at the surface do. And in fact, what seemed to be the most sort of conducive thing to feeding them happened to be sort of accumulated, agglomerated organic matter, or essentially marine snow. And in the Gulf of Mexico, we actually replicated these results where when we went out and collected these guys, they really would not hold on to any copepods or artemia or anything like that. And they really, really had a strong affinity for marine snow, basically, for groupings of organic matter. And in fact, we were able to grow these species for more than 3 to 4 months, actually, much longer than what we typically think of as a typical lifespan for Planktiform Minifra. Another line of evidence is barium concentrations in these subsurface globorotalids. So here's a plot from a paper by David Lee and Ed Boyle in 1991, showing really elevated barium calcium signatures in globorotalids relative to more surface ocean foraminifera. And they attributed this to changes in the potential mechanisms of calcification and vital effects in the species. However, we do know more recently with a lot more culture data, here's a paper by Jennifer Fernbacher and others in 2018, where they showed for Neogloboquadrina deutertri, which is not a globorotallid, but it is a subsurface dweller, they actually showed that these elevated barium calcium ratios is actually evidence for an organic aggregate microhabitat. So this is remarkable to think of, that essentially these subsurface dwellers, the globorotalids or deutertri, that they're not just living in the subsurface, but they're living within marine snow in the subsurface. Okay, so they really are glomping on to the marine snow. And essentially what we're proposing here is that if we see that their abundance declines, that has to be related to changes in the export of primary production, and particularly of particulate organic matter. Okay, and finally, we also have a proxy for paleonutrients. We're measuring the cadmium to calcium ratios in G. ruber. So now we're moving back to G. ruber, which is that surface ocean bug. And this proxy is basically founded upon the strong correlation between cadmium in the oceans, which is a micronutrient by itself, but its correlation with phosphorus. So here's seminal work by Ed Boyle in 1988. Fast forward to 2015, here are some really nice profiles of dissolved cadmium in the oceans right here. And you can kind of see how it really nicely mirrors the phosphate concentrations in the ocean as well, where phosphate is obviously a major macronutrient. And finally, here's a paper by Ripperger and others in 2008, essentially showing how cadmium calcium in foraminifera actually reflects phosphate composition. And I'm not going to go into very many details here, but I'm happy to chat with those who may have questions about this. So essentially, we're going to use CDCA in the surface ocean as a proxy for nutrients. Okay. All right. I've been talking about all of this. Let's get to some results. This is a picture from Expedition 353. Here's our co-chief, Steve Clemens, showing some really exciting results of mud that came out. Okay, so we're going to be looking at Indian monsoon variability since the last glacial maximum. Here are the different sites that I'm going to be showing you. Essentially in the marine realm, I only have one other record to compare our resolution to. This is basically work from Rajiv Saraswat and others in the sort of the Malabar coast region. And so these are the two marine records that I'm going to discuss. Both of them also have really high resolved centennial scale delta 18 and paired magnesium calcium, similar to our approach right here. And I'm also going to show you all of these disparate speleothem records, cave speleothems, which their isotopic composition is thought to reflect the isotopic composition of precipitation over the caves. And essentially, we've kind of compiled all these records, and we want to see how that looks like for the LGM to present. Okay, so I'm going to start off by showing you the speleothem records. So these colors are representing where they're coming from. So here are reconstructions from Bittu and Sahia in the Himalayan foothills. Here's Mamlu Cave right here in the yellow, orange, and red. And then here's another record from Kutumsar. I've actually ignored, there are a bunch of other Speleothem records, but I've ignored them because they don't span at least 2,500 years. That was kind of the cutoff for inclusion over here. And essentially also I have precession that's plotted up here, where negative precession minima is going to correspond to northern hemisphere summer insolation maxima. And the other thing I want to show you is that I've actually, the scale right here is nonlinear. I've just done that to make sure that we can look at the Holocene in detail, as well as the deglaciation. Now, the main take-home message for these Speleothems is that they are all over the place when it comes to what they collectively indicate for changes in the Indian monsoon domain. The signatures are arguably more coherent during the deglaciation, but then in the actual Holocene, interglacial, they actually separate sometimes by up to several per mil. I've tried to mean normalize these as well. Obviously, they're coming from different heights, and so they're going to have different mean states, but let me reassure you that their variability doesn't match either. But that's okay, because these are basically point representations of the isotopic composition of rainfall, and they also may have impacts that are related to cave processes. So for example, you can see here there's about a 2 per mil difference in Speleothems coming from the same cave. So this really is not this hasn't really painted a cohesive picture of monsoon variability from 20,000 years ago to present. Okay, now I'm gonna layer on our reconstruction right here. So what I'm showing you is each one of these diamonds is a paired magnesium calcium delta ATNO measurement. And I am showing you here the delta ATNO of IVC, which IVC stands for ice volume corrected. And essentially what we're looking at here are variations in the local hydrography of delta ATNO. So this is really our monsoon record that we're looking at here. So a couple things immediately pop out. We have a very interesting sort of glacial structure that is probably familiar to many of you. And over the Holocene, we don't necessarily see this sort of 1:1 decline with summer insolation. We definitely see an overall decline with really high values of runoff or low values of delta ATNO during the early Holocene, and then lowered runoff during the late Holocene. But as you can see, this record is basically telling us that it happens in the states of fits and bursts, and not necessarily a steady gradual decline like we've observed in different regions that actually mirrors insolation. Okay, so that's an important takeaway here. Another takeaway is that the early Holocene seems to be the time where we have the maximum runoff, and the Heinrich event right here from 17 to 15 is when we actually have the lowest runoff, or the most saline, corresponding to the most saline conditions right over here. Now here is the record from the Malabar coast right here. And this is SK237. Again, this is the delta ATNO of ice volume corrected variations that represent variations in the local hydrography. And you can kind of, and here are delta ATNO observations at the particular sites right there. And the triangles represent the age control points. Okay, so we kind of see that there is, again, coherence in the deglaciation. But all of these records are basically telling us different stories when it comes to the Holocene. There are some correspondences here between some of the Speleothem records and our record right here. Most notably is sort of this dip and deficit in runoff during about 4,000 years ago, which again might sound familiar to some of you. And then we have sort of these multi-centennial scale deficits that punctuate the steady Holocene mean. And then finally, towards the last 2,000 years or so, we see a decline that actually seems to be mirrored in the Arabian Sea record and some of these Speleothem records as well. Now, one thing I'd like to point out, though, is that either way you look at it, we're not seeing similar trends across the board for the Holocene. And this really talks about increased spatial variability of the Holocene, of the Indian monsoon over the Holocene, where perhaps there was a lot more coherence during the deglaciation relative to the Holocene. And in fact, we're actually seeing opposite trends here, where this record is actually suggesting, a freshening, or at least lower delta ATNO, trending values towards lower delta ATNO seawater values over sort of the early to mid Holocene, whereas this is pretty much different. So my point is that essentially the monsoon records don't really show a 1-to-1 response to precession. And B, the deglacial signal is more spatially coherent than the Holocene signal. Okay, so what does that hold for paleoproductivity? Remember that the peak monsoon was early Holocene, and the monsoon failure we saw during the Heinrich event. Now, the paleoproductivity monsoon linkage, I'm just putting two papers out here that have been published fairly recently, where both of these sets of authors have essentially identified that productivity actually increases during the glacial period and productivity decreases during the interglacial period. And the mechanism invoked by these authors right here is very similar to the mechanism that is observed in the modern during the sort of the post-monsoon outflow season, where if you have strengthened runoff from the into the Bay of Bengal, which we do during the interglacial periods, that you essentially restrict productivity by having a thick barrier there. Okay, so this is kind of the paradigm and the expectation. So what do we see in our results? So what I'm showing you here is a smooth version of the Delta 18 seawater record in blue right here with its uncertainty envelope. Again, the Heinrich event being the period of lowest runoff and the early Holocene being highest runoff. On top right here is the SST reconstruction from the same site. It's based on magnesium calcium. And again, it's smooth in the same way. And here is our productivity indicators right here. Okay, so in green is the cadmium calcium reconstruction from the surface ocean. And in brown right here is the relative abundance of the globorothalid species. Okay, so this is what we're inferring as a proxy for particulate matter export into the subsurface and ultimately the deep ocean. And this cadmium calcium is a proxy for nutrients basically in the surface ocean at this particular site. And so you can see that not only are they coupled fairly tightly across the span of our record, but most intriguingly, we actually see that there are productivity collapses. These species go down to zero, almost zero. There's hardly any to be found. These entire, not just species, these are the genus, during both monsoon failure as well as monsoon excess. So this really points to some stark nonlinearities between the monsoon biogeochemical linkages in the Bay of Bengal. So we're seeing that in the early Holocene, strong monsoon, we see a productivity collapse that is in line with expectations from before. But during the Heinrich event, when we have really almost no runoff at all, which is what certain models, high-resolution ocean models in the Bay of Bengal actually agree with this value. They basically say that during the time of no runoff, we also have a productivity collapse. Okay, so what is really driving this? So what we decided to do was to essentially measure individual foraminifera during these three particular periods. And we measured across two different species. So the dashed line is telling us about G. ruber in the surface ocean, and the thick line is telling us about individual foraminiferal analysis for T. sacculifer, which also lives in the surface ocean, but slightly deeper than G. ruber, maybe about 15 to 20 meters, depending on who you ask, maybe slightly more, but again, in that sort of mixed layer region. So what are we seeing? We're basically seeing that they both of these species mirror each other in their distribution for the Holocene. And during the early Holocene, where we're seeing really, really intensified runoff. And if you recall from this plot, the more negative we go, the individual foram signature is really sensitive to that runoff signature. But on the flip side, when we move into the Heinrich event, we actually see a disparity in the distributions where there is significant difference between the medians of the sacculifer species versus the ruber species. So you can see how this separates out during the Heinrich event. Okay, and as you recall, if we move towards the more positive side, then we're temperature sensitive. And essentially, this is pointing towards thermal stratification in the topmost part of the water column, whereas both of these creatures are essentially telling us that there was salinity stratification during the early Holocene. So let me just wrap up here with the proposed mechanisms of what we think is going on here with all of these different data sets. Okay, so here is our reconstructions put together. And if we focus on the late Holocene, this is the sort of the distribution that we see where the ruber and the sacculifer distributions mirror each other. And what we think is going on here, this is the same schematic from before, based on actual profiles. So you can see here that in this isothermal layer depth is where both rubers as well as seculifers are going to live. And this is today, and we see that the barrier layer is about 20 meters or so. I'm sorry, the barrier layer is this, so it's about 15 meters or 15 to 20 meters. We have a mixed layer about 20 meters based on density. And we have a deep chlorophyll maximum somewhere from 60 to 80 meters or so that is really sensitive to changes in the barrier layer, okay? And both of these give us the same type of distribution. Now, when we look at the early Holocene, okay, we see really high really low delta Tino values and high monsoon runoff. And we see, again, a complete collapse in the globorothalid population, but also in the cadmium calcium. And these two species, their individual foraminiferal signature is telling us that there is really strengthened seasonality here. These tails are larger by almost by per mil and a half, where a large portion of that cannot be explained by temperature. It has to come from changes in runoff. And so our proposed mechanism for the early Holocene is a much thicker barrier layer that's driven by a thicker freshwater cap. And also concurrently, you're going to have a larger isothermal layer depth, given that the other side of this distribution is also mirroring each other across both of these species. So during monsoon intensification, just like the other authors proposed, we have salinity stratification and a productivity collapse. Now, on the flip side, when we move into the Heinrich event, we are actually proposing here that there is a permanent erosion of the barrier layer. Because of the significantly throttled runoff into the Bay of Bengal stops behaving like the unique scenario that it exhibits today, and it is going to be more. The coastal Bay of Bengal is going to be more similar to sort of an oligotrophic open ocean condition, and due to summer sort of solar heating that is at play, but with the lack of runoff, we actually see this huge thermal stratification in the very topmost part of the water column. So our proposition here is that the salinity profile right here becomes something more similar to an open ocean condition. And in fact, then the density actually mirrors the temperature. And you basically have thermal stratification that's being driven by, it's almost like the coastal Bay of Bengal becomes like a pond. And this is really, really significantly different compared to what it is today. And this essentially, our proposal is that this collapses the globorothalid populations and the cadmium calcium ratios as well, because you don't necessarily have enough of the wind pumping because of the failure of the monsoon, but you also have this thermal stratification that inhibits mixing and sourcing of nutrients from the subsurface into the surface, from the deep ocean into the subsurface ocean and the surface ocean, and that in turn then collapses productivity. So finally, we come back to these model simulations. Here's Katzenberger and others looking at the sort of the robust increases that are projected for the monsoon. And here's this paper by Kwiatkowski and others for CMIP6 and the culmination of several different models looking at the net primary production in the Bay of Bengal, actually showing an increase relative to today in the future. So the deep sea record essentially suggests buyer beware. Take some, you got to be cautious in this interpretation of taking these ESM responses at face value, because these two things do not necessarily jive together. Okay, so I will just recap here and provide some take-home messages. And so I want to start off by showcasing that we have a centennial scale runoff reconstruction from site 1446 that demonstrably shows that it captures Indian summer monsoon variability in the modern and going back in time. And the compilation of records across the subcontinent that have similar resolution to our reconstruction, they're all suggesting a nonlinear response to precession, or at least a complex response that doesn't, for example, look like what people have been inferring from, say, East Asia or the Middle East, for example, from speleothems. Okay, the second sort of major take-home message here is that we find that productivity collapses during both monsoon extremes. During the period of strengthened ISM seasonality, which we saw both from our delta 18 seawater reconstruction, but also from the individual foraminiferal analysis during the early Holocene, but productivity also collapsed during monsoon failure. And we suspect that stratification really drives both of these scenarios, but stratification was different during both of these time periods, where you have salinity-driven stratification forced from runoff during the early Holocene and temperature-driven stratification during Heinrich Event 1. And finally, the modeled response of increasing net primary production in the Bay of Bengal, as well as a stronger monsoon that's projected in the future, they seem to be at odds with each other if you look at the deep sea record. So with that, I'll stop right here. Thanks everyone for your time, and I'm happy to take on any questions.
Thank you very much, Cal. So yes, we do have one question here from Rajiv Saraswat. Rajiv, do you want to ask your question, or shall I read it for you?
Yeah, Peter, I'll just ask. Kaustubh, thanks a lot for a nice presentation. Can you hear me?
Yes, thanks.
Yes.
Yeah, Kaustubh, several questions. I don't know. I mean, is it okay to put too much of emphasis on the barrier layer? Because in this part, there are a lot of other factors which are also responsible for not only nutrient input, but taking those nutrients down. I hope you know the eddies, which play a very, very crucial role. There are several papers which have come up that eddies are the main reason for sustaining the oxygen, low oxygen, or say relatively higher oxygen concentrations. Also the submarine groundwater discharge, the huge riverine runoff. I don't know, under that scenario, how okay is it to put too much of emphasis on the barrier layer?
Yeah, that's a good question. So just to repeat the question, I think the question is, how can we pin everything on the barrier layer as opposed to these different processes that affect productivity as well in the Bay of Bengal? So the certainly the major sort of promoter of production in this region is eddies. Clearly, I mean, there's more than enough evidence, like you say, rightfully so, that eddy pumping or sourcing from the subsurface through a variety of different processes. I mean, through nearshore winds, through even remote forcing, even from the central equatorial Indian Ocean, from Kelvin wave propagation as well. Now, what we are proposing here is not inconsistent with any of those aspects. So regardless of these different prospects, you still need to have some erosion of that barrier layer from these eddies if you want to source nutrients from the subsurface or from the deep ocean into the subsurface ocean. So, basically what I'm trying to say here is that all of these processes act together on these geological timescales for us. And so the riverine input, several papers have also shown that riverine input is really, really restricted the nutrients to sort of the estuarine region and doesn't make it out into the coastal Bay of Bengal, even into the open ocean. But even if you take that as a huge influence of nutrients in the Bay of Bengal, basically our single foraminiferal analysis coupled with the globorotalids are saying that during this period of really strengthened runoff, we're not seeing if this was even somewhere up here, then I would be remiss in this interpretation. But we see values go back to 0. And so I really think that the barrier layer plays a significant role here, in line with the previous studies, for example, from Silva and others, as well as from Phillips et al., that talk about the stratification domination during interglacials that caps productivity during the glacials. So I agree with you that eddy pumping is the major mode. But I'm also saying that all of these factors are constructively interfering during these geological time periods.
Okay, and also I'm a bit surprised that you're using the globorotalids for productivity. Why not boloides? We have enough of boloides because one of my students worked on the entire hole, and then we are getting pretty good amount of the boloides.
Right. So the question is. Yeah, so the question is, why do we use globorotalids and not boloides? It's actually a good question. We actually have full species assemblages on this. I can go into the details maybe with you in a personal conversation, but let me just say that we know that the Bay of Bengal is not a significant upwelling region. Okay, so given the classical boloides upwelling sort of connection, that's not necessarily going to work here. But B, we also see that boloides and deutertri, they mirror each other. Okay, and when they, in terms of their signatures, and even though they actually show very similar variability for the earliest Holocene, for the Heinrich event, So they also all go down during the Heinrich. Boloides, deutertri, as well as the globorotalids. They show different signatures as you move into the Holocene. And the deutertri and the boloides are more coupled. And I think that might actually have to do with some responses of the potentially increased nutrient input from the ocean, from the river into the Bay of Bengal. But regardless of what you do, the globorotalids being in the subsurface, if they're dwelling on these particulate organic matter, they're not going to be happy if there's not enough production. So that's really the connection here, is the production. And moreover, boloides and deutertri, for example, we know boloides is more of a hunting species. I mean, they're predatory, as opposed to these globorotalid species that are more passive.
Okay, we have another question here from Sudhir Badra. Sudhir, did you want to ask your question?
Hi. Actually, am I audible?
Yes.
Yeah, we can hear you.
Yeah. So that's a really good presentation. I got to see a lot of things. Just one thing is that you have used the globorotalia species, which is thermocline dweller, like it is significant thermocline dweller. But the barrier layer can act as a trap to nutrient in the thermocline, so that the globorotalia species can increase. So you talked about the marine snow coming from the surface layer. So how do you know that the increase is because of the mixed layer productivity or thermocline productivity?
Yeah, it's a good question. So the question is, why? How do we know that the globorotalids are responding to, or which one are they responding to, mixed layer or subsurface? Well, so we have oxygen isotopes and carbon isotopes on globorotalids as well that tell us that they're living deeper than the deep chlorophyll maximum, somewhere at the deep chlorophyll maximum at our location, or slightly deeper. So essentially, they're integrating, and the deep chlorophyll maximum is beneath the thermocline as well, the start of the thermocline. So essentially, it doesn't matter. It's both. It's all of the above. They're essentially, what I think is that if there is organic matter that's coming from anywhere above them, they're happy. But if there's not, they're not happy. And so I really think that given their depth beneath the deep chlorophyll maximum, it is basically representative of all of the production above them, basically. So both the mixed layer as well as the subsurface production changes should be reflected in these globorotalid species. And I'll just point out that, I don't think that this is necessarily a quantitative proxy per se. And that's why I'm not necessarily inferring too much or dwelling too much on the increases of these relative abundances, but more so what is really striking is the absence of these guys. Okay, so that's the real take-home message here, is that we're interpreting the absence of these species as opposed to the relative absence, as opposed to their abundance, which probably does say something about increased production, but it is going to be a more difficult thing that requires more work to actually quantify that. So I hope that answers your question.
And I think we've got time for one more here. Mark, you, would you like to ask your question?
Hi. So my question, it kind of piggybacks on a lot of the previous ones with the thermocline species and your cadmium calcium measurements. But I'm actually really glad that your cadmium calcium measurements came out with a fairly good signal, because I'm working on cadmium calcium in the Maldives as well. And since we have such low nutrients, a lot of this, I'm getting like 0.04, 0.02, it's very minuscule between glacial and interglacial cycles. So I guess you picked a good spot to do cadmium calcium. But so why don't you do the cadmium calciums on the thermocline species instead of the surface species? You'd be comparing apples to apples and not apples to oranges.
Yeah, no, that's a really good question. I think more than anything, this was from a perspective of logistics more than anything else. So something about globorotalid-based cadmium calcium, that's coming up next. I mean, that should definitely be future work in progress. But one of the other reasons was that we wanted to really look at the surface ocean signatures. If we were to assume that cadmium calcium is a reflection of micronutrient sourcing to the surface ocean first of all, and whether that can say anything one way or the other about just in general sourcing of nutrients in the upper part of the water column for the Bay of Bengal. So definitely, we would be very interested to see what the global artalid cadmium calcium looks like, and that's going to be potential future work. So hopefully, hopefully we're going to see very nice glacial interglacial cycles with your record as well.
Thank you very much. So we should probably wrap this up now. I just have a couple of announcements. First of all, if you would like to speak in this series, you should send an email to myself or Liviu or Tara and let us know that you'd like to do that and give us a prospective title. You can also check out the updated website that has all the talks through to spring next year, now has recently been updated. If you want to be added to the weekly email reminder, send me an email and I will make sure you get on that list. And I just put my email in the chat there for you, as well as a link to the seminar website. Fine, last but not least, come back next week. Ed Hathorn is going to be entertaining us. It's at the other time, remember? We alternate. This is the North American friendly slot, Schedule A. Next week is the sort of Asia-friendly slot, Schedule B. So please come back, and your host, I believe, is Tara Janelle next week. Please join me in thanking Cal for his splendid presentation. Thank you very much, and I look forward to see you all again before too long. Thank you.
Thanks, everyone.
Thank you.